Hello viewers, good morning. It is T. N. Oza here. Today I am going to present a new video on the topic Beer-Lambert law. This topic is of fundamental relevance and practical utility. Under this topic, we will be discussing the following points. Introduction to Beer-Lambert law, mathematical formulation of the Beer law, experimental design, transmittance, deviations from Beer law and limitations, graphical display, applications of Beer law, and some numerical problems. Introduction to Beer-Lambert law. When light of a suitable frequency is allowed to pass through an absorbing medium, a very dilute solution of the sample substance, several phenomena such as reflection, refraction, scattering, and absorption take place. A law of much practical utility in the field of absorption spectrometry and photochemistry is the Beer-Lambert law, often referred to as the Beer law. This law relates the magnitude of absorption of light by the sample with path length traveled by the light beam, concentration of the absorbing substance in the solution, the intensity of the incident light, the refractive index of the medium, and the functional nature of the sample molecules or ions as the case may be. It finds routine applications in quantitative assay of certain substances like pollutants, drugs and pharmaceutical formulations, foodstuff adulterants, chemical reactants, rare reagents, impurities in the air, water, and soil, etc., in chemical research laboratories, agriculture related analysis, food and drug analysis, biochemistry, physiology, clinical chemistry, forensic science, neuroscience, and pollution control establishments. Provided that the requisite precautions are strictly followed, satisfactory results are obtained from the Beer-Law experiment. In addition, the simplicity of Beer-Law experimentation makes the technique quite popular. The main fundamental equation of Beer-Law is A equal to epsilon Cb, as given in the previous slide. How this equation results can be understood with reference to the following line diagram. In this diagram, we have shown a quartz tube of width d. This tube is filled with the experimental solution. Concentration is indicated by the letter C. Monochromatic light of initial intensity I0 is allowed to pass through this sample. Some part of it may be absorbed, and the remaining part, which is transmitted, is represented as IT. The whole path B is divided into infinite number of very thin layers dV. The light which just enters this layer dV is given the intensity I prime. A very small portion of light is absorbed. Therefore, the emergent intensity is I prime minus di prime. In this expression, the unitless parameter A is called absorbance. A equal to epsilon Cb. A is called absorbance. It is unitless parameter. It is absorbance of the sample. It represents a decadic logarithmic function, log base 10 I0 over IT. In order to be convenient, this whole thing has been replaced by a single letter, absorbance A. The emergent light is shown as IT. There is another equation which is useful. IA equal to I0 minus IT. Here IA is absorption. This term is a bit different from absorbance. Absorption IA equal to initial intensity I0 minus transmitted intensity IT. This equation also finds use in many calculations. In the expression 1, as I told earlier, the letter C stands for the molar concentration, molarity, M of the solute, and B is the path length in centimeter. That is the width of the quartz cuvette in which the solution is filled. The symbol epsilon is called molar absorptivity. From equation, it is clear epsilon equal to A over CV. The unit of epsilon is mole inverse, liter, centimeter inverse. In brief, it can be written as molarity inverse and centimeter inverse. Actually, epsilon is the ratio K over 2.303. Here K is called absorption coefficient. In most of the calculations, K is used. So K and epsilon both are related. Both are actually the same thing. Epsilon, a single letter, has been used in place of K by 2.303 just for convenience. The intensity of light beam is defined as the energy or the number of photons incident on the sample per unit area per unit time. The probability that photons of a beam of intensity I prime will be absorbed by the sample molecules or ions is directly proportional to the concentration C of the solution and the thickness B of the absorbing medium. This can be expressed by a differential equation minus di prime over dv proportional ci prime, equation 3. By putting a proportionality constant, you can write minus di prime over dv equal to k ci prime, equation 4. This equation implies that when the beam of intensity I prime is falling on the absorbing medium, each infinitesimally thin layer dv of the medium reduces its intensity by a definite proportion, that is di prime over I prime. It is not the same as a fixed amount. Be very clear about it. Suppose the intensity is initially 100%. The first layer absorbs 2%. Then the second layer will absorb 2% of 98%, and so on. Equation 4, look at equation 4. On the left hand side of this equation, there are two variables, intensity and B. On the right hand side, there is only one variable, intensity. Because we need to integrate this equation, this has to be rearranged so that on each side we have only one variable. On rearranging equation 4, we get equation 5. The beauty of this equation is on the left hand side, you have only one variable, intensity. On the right hand side, you have only one variable, B, width. Therefore, this equation can easily be integrated. Experimental design. Here, a quartz cuvette of width B, whose limit is from B equal to 0 to B equal to B, is filled with a very dilute non-viscous solution of experimental substance at a concentration C and a constant temperature. A monochromatic beam of visible light if the sample is colored, or UV light if the sample is colorless, of initial intensity I0 is allowed to traverse through the solution width B. K is a proportionality constant, as I said earlier. It is characteristic of the functional nature of the substance. Lambert Law states that every infinitesimally thin layer dV of the absorbing medium reduces the intensity by a constant proportion di prime, but not a constant magnitude, as it passes through the various layers dVs. So the intensity is reduced by a constant proportion di prime over I prime. Thus, the rate of change of intensity may be defined as minus di prime over dv proportional to I prime. Beer-Law states that rate of decrease of intensity minus di prime over dv is also proportional to the concentration C, provided that solution is very dilute and the substance absorbs the radiation of that particular wavelength but does not undergo any chemical or physical change like dissociation, association, conformational change, etc. during the experiment. Combining both laws, that is Lambert law and Beer-Law, gives equation 5 Ti prime over I prime equal to Kc dV, equation 5. In equation 5, K and C are both constants for known solution, while both I prime and B are continuously varying between the limits. Two limits are as under. At B equal to 0, I prime is I0. I0 is a constant because it is initial intensity. And at B equal to B, I prime becomes IT. Here you see IT is variable, I0 is constant, B is variable. Therefore, using these limits, integration of equation 5 can be done, and the results of integration are equation 6 minus ln IT over I0 equal to ln I0 over IT equal to KCB. For bio students, it is necessary to know that integration is of two types, definite integration and indefinite integration. When we are using limits, integration is called definite integration because there is no uncertainty in the result. When we are not using limits, then the whole series of results are possible. Therefore, integration is called indefinite integration. If we carry out indefinite integration, we get minus ln I prime equal to KCB plus m double prime. Question 7 is the result of indefinite integration. How is this integration carried out for bio students only? Bio students are already familiar with this. This is based on the simple rule that integration of 1x with respect to the variable x yields ln x plus an arbitrary constant say m. And similarly, integration of dx gives x plus an arbitrary constant m prime. The two constants m and m prime can be put together as m double prime, and upon putting the limit b equal to 0, I prime becomes I0, so that m double prime becomes minus ln I0. The value of m double prime can be put in equation 7 to give equation 6. On changing to decadic logarithmic equation, 6 becomes log base 10 I0 over IT equal to KCB over 2.303, equation 8. The left hand side of equation 8 is defined as absorbance, the unitless parameter, characteristic of the functional nature of the compound, and putting both constants k and 1 upon 2.303, a single constant epsilon, the molar absorptivity, we derive log 10 I0 over IT equal to absorbance equal to KCB over 2.303 equal to K equal to epsilon CB, equation 9. For evaluation of the variable IT, equation 6 becomes ln IT over I0 minus KCB. This logarithmic equation can be written in the equivalent exponential form as IT equal to I0 product e raised power minus KCB. Using decadic logarithmic system, IT equal to I0 into 10 raised power epsilon CV, equation 10. Transmittance. Another useful parameter called transmittance T is defined as IT over I0 or percent T and 100 IT over I0. This can be related to the absorbance A as follows. Taking log both sides gave log T equal to minus A or A equal to minus log T equal to log 1 by T, equation 11. In the exponential form, T equal to 10 raised power minus A equal to 10 raised power epsilon CV, equation 12. Alternatively, log 100 IT over I0 becomes log percent T equal to log 100 IT over I0 becomes 2 plus log IT I0. This is 2 minus A. A is absorbance. By transposing, A equal to 2 minus log percent T or 2 plus log 1 upon percent T. Question 13. This is to emphasize here that we are using so many equations. Essentially speaking, we are using only one equation, A equal to epsilon CV. For solving numerical problems in different ways, we need modified equations. So all these 13 equations are not different, they are interrelated. Therefore, you need not worry about them. There is only one fundamental equation, A equal to epsilon CV. For solving various numerical problems, we have to modify those equations in a number of ways. Simple arithmetic, simple calculus. Deviations from Beer law and limitations. Beer law is found to deviate if the solution concentration is not very dilute, or there occurs some kind of physical and or chemical change in the material upon absorption of radiation. Presence of extraneous matter, fluorescent substance, X-ray radiation, reactive solvent, or changing temperature during the measurement can be another cause of deviation. At higher concentration, the refractive index eta of the solution also changes. It has been found that it is the quantity eta over eta plus 2 square multiplied by epsilon rather than epsilon that remains constant. Another cause of deviation is the interionic repulsion, which can drastically change the absorbance of the solute. The following graphs are self-explanatory. Graph 1, it is a graph between absorbance along y-axis, concentration along x-axis. A straight line passing through origin means ideal situation, no deviation. The angle theta, tan theta gives slope of the line from which molar absorptivity epsilon can be obtained. Note here that the inclination angle is always measured in the anti-clockwise direction. The arrow indicates it. So graph 1 is for ideal condition. Essentially speaking, ideal conditions for Beer law don't exist. The second graph, again between absorbance and concentration, is showing negative deviation at higher concentrations. In some cases, deviations may be positive. Magnitude of deviation depends on situations. The third graph is between percent T and concentration. This graph does not yield a straight line, therefore it is of less importance for calculation purposes. If we need to carry out calculations, we have to draw tangent. Applications of Beer law. In the previous slide, the first graph is very useful. Suppose we have a series of solutions. Some concentrations are known, some are unknown. Absorbance can be measured for all. So a plot between absorbance and concentration gives a line. From that graph line, unknown concentrations can be determined. Secondly, if concentrations are known, absorbances are measured, then a graph can produce epsilon. very important parameter. The slope of the line is equal to k over 2.303 or epsilon. So most applications of Beer law are about determining unknown concentrations of very, very minute quantities like pollutants, like adulterants, etc. The cuvette widths B can be eliminated using reference samples. Alternatively, if a series of standard solutions and few unknowns are used, the unknown concentration C can be determined. Here we are giving some numerical problems. If you solve numerical problems, you can easily remember the equations, you can easily understand the mechanism, you can easily understand the procedure. Here we have given a numerical problem. Phenolphthalein forms a complex with iron second. What data are given here? Molar absorptivity epsilon is given. Absorbance is given. Width B is given. We have to determine C. Look at the equation A equal to epsilon CB. A is given. Epsilon is given. B is given. So C can be readily calculated. It is 1.25 into 10 to the power minus 5 molar. The thing here to note is this lower concentration cannot be readily determined from normal routine chemical methods. But using this Beer law experimentation, this much lower concentration can be determined. Another numerical problem, in a Beer law measurement, the sample solution absorbed 10% of the incident light. In another experiment, the path length was tripled, while all other conditions like concentration, temperature, wavelength, intensity of light changed. Now we want to know what percentage of the incident light will be absorbed. How to solve this numerical? A1 equal to log I0 over I1 equal to KBC by 2.303. In the next case, the B value has been tripled. So A2 becomes 3A1. Very simple. Because B has been increased thrice, so A2 becomes 3A1. Now, putting I0 equal to 100 and 10% is the absorption. So I becomes 100 minus 10 equal to 90. By taking log values, we can determine A2 equal to 0.1374. And you know the definition of absorbance, log I0 upon I. So by taking anti-log both sides, we can get I0 over I equal to 1.372. Reversing it, I upon I0 becomes transmittance equal to 0.73. Hence, the fraction of light absorbed is 1 minus 0.73 equal to 0.27. And width of the quartz cell is 5 times. Fraction of light absorbed is 0.41. So you see, absorbance is directly proportional to B. Here, one very important point, suggestion rather, I would like to give. The students should be familiar how to take log, how to take anti-log. Sometimes they hesitate. These things are not very difficult. You can readily learn it, practice it. Any simple book can provide you the means. There are 3-4 rules about logarithmic relations. Then you must be very conversant with how to look at table for determining log values or anti-log values. And the 4 basic rules, log A multiplied by B equal to log A plus log B, log A power C equal to C log A, log A over B equal to log A minus log B. These are some of the rules. Similarly, natural logarithm is converted to decadic logarithm by multiplying with 2.303. Another numerical problem. In a Beer-Law experiment using cell width 2 cm, the transmittance was 0.01 molar of solution X and 40% of the same concentration for a compound Y. 30% for Y, 40% for X. Now what we have to do? We have to calculate the transmittance for a solution in which both X and Y are present in equal concentrations. So a new point here to learn is Beer-Law is additive, that is A equal to A1 plus A2. Everything is very clear here. The final result comes out to be percent T equal to 12. One more numerical problem. How to calculate epsilon for a series of solutions of the same substance. So here you see B is given, C is given, I is given, I0 is 100%. From this we have to calculate epsilon. So very easily we can calculate that because the fundamental equation A equal to epsilon Cb is there. So epsilon equal to A upon Cb. For another case, absorbance is given, and remember, in this case, absorptivity epsilon is represented by another letter A. Sometimes in examination, this kind of trick is played. So you should be familiar. Just follow the name, not the symbol. B is 1 centimeter. We have to calculate A. We have to calculate concentration C. Formula is concentration equal to absorbance over AB. Here small a is epsilon. Another problem is epsilon or small a is given, B is given, concentration is given. We have to calculate. So last question, as I told in equation 2, IA is also an important parameter. So IA is equal to I0 minus IT. We have to simply put the value of IT to determine IA value. Thank you very much. I am hopeful if you go through this video 2-3 times and read properly, you can understand Lambert Law, its applications. Thank you very much. Thank you once more.